Welcome! In this video, I'll show you how to use AWS X-Ray to analyze the performance of a distributed application. This diagram shows the architecture for a version of the Cafe website. This version of the website is more fully developed than the one you have built in the course labs up to this point. In this version of the application, AWS Lambda functions have been built to be invoked when users request information on the Cafe website. These Lambda functions invoke the REST API endpoints that you created in the Lambda lab earlier in this course. For example, when a user loads the Cafe homepage, the getProducts Lambda function is invoked. It performs a lookup in Amazon DynamoDB to retrieve the menu items. Also, as you will see in this demonstration, after authenticating to the Cafe website, an employee can request an inventory report. The request invokes the createReport API endpoint, which in turn invokes a state machine that is defined in the AWS Step Functions service. The state machine runs a workflow that consists of a series of Lambda functions. The functions query an Amazon Relational Database Service, or Amazon RDS, database for the latest report data, and then compile and deliver the report. In this demonstration, I'll configure X-Ray to provide a view of the getProducts API endpoint call results and an end-to-end view of the createReport API endpoint requests. With these views, I'll be able to see the performance and latency statistics of the different services and components involved in these parts of the Cafe's distributed application. Okay, let's get started. So here I am logged in to the AWS Management Console. First, I'll go to the X-Ray console. Notice the links on the left, including service map and traces. As I choose these areas, you see that no data is collected yet. That's expected though, because I haven't instrumented my distributed application yet. Next, I'll go to the Lambda console. Here you see that many Lambda functions are defined. The getRealData function pulls the coffee suppliers data from the Amazon RDS Aurora serverless suppliers database. The function then invokes the generate pre-signed URL function and the generate HTML function. All three functions are invoked when a report is requested. Separately, the getAllProducts Lambda function retrieves Cafe menu data and displays it on the Cafe website homepage. First, I'll enable active tracing on the getAllProducts function. I choose the function, choose configuration, and then monitoring and operations tools. I'll edit these settings. Then, under AWS X-Ray, I'll set active tracing to on and save the change. Next, I'll follow the same process to enable active tracing on the other three Lambda functions. I'll enable it on the getRealData function, and I'll enable it on the generate pre-signed URL function. And finally, I'll enable it on the generate HTML function. Great. So now I have 4 Lambda functions that X-Ray will collect tracing data for. Now let's go to the Amazon API Gateway console and enable X-Ray tracing here as well. I'll choose Products API and choose Stages, then Prod, and then the Logs Tracing tab. Here I'll choose Enable X-Ray Tracing and save the change. Finally, I'll go back over to the Resources view and deploy the API change to the prod deployment stage. Now, I'll head over to the Step Functions console to enable X-Ray tracing there as well. Recall that the createReport API endpoint will invoke the state machine defined in Step Functions. The state machine will then call the Lambda functions, so it will be helpful to enable X-Ray tracing here as well. I locate the state machine and choose Edit. Then I scroll down to Tracing and choose Enable X-Ray Tracing. Notice the message that displays. To do tracing, X-Ray must have permissions. That's true of all the AWS Identity and Access Management, or IAM, roles that control the permissions of these services that I'm enabling for tracing. They all must have permissions to connect to the X-Ray service. Let's save this change and I'll show you an example of those IAM permissions. Let's return to the Lambda console. Here, I'll choose the getRealData function, configuration, and then permissions. Notice that this function uses a role named role for all lambdas. I'll select that and it takes me to the IAM console. And here in the permissions tab for this role, I'll expand the policy and look at the JSON. Notice that this policy grants X-Ray permissions to the role. That will allow the role to write trace data to the X-Ray service. In a true production environment, I would want to lock down these permissions more tightly, but in this test environment, this will suffice. All the roles that apply to the Lambda functions, Step Functions State Machine, and REST API that I've instrumented also have a sufficient level of X-Ray access granted to them for this demonstration. Okay, so now that I've instrumented the Lambda functions, REST API, and the state machine, I'm ready to run some tests. I'll use the AWS Cloud9 IDE to do that because it has a convenient bash terminal that already has account credentials configured in it. However, before I run the test, I need to gather some information from the API Gateway console. I'll choose the products API, and now I'll choose get under products. I need to capture the REST API ID and the resource ID, which are both shown here in the URL. In the text editor, I've already written the command that I will run in the terminal, but I wanted to show you where I got the ID numbers that you will see in the command. Okay, so I'll return to the AWS Cloud9 console and open the IDE where I can run some tests. This code I just pasted in uses the AWS command line interface, or AWS CLI, to test invoking the get products API endpoint. Notice the REST API ID and resource ID values. They match the ones I just showed you in the API Gateway console. This AWS CLI call is wrapped in a simple loop that will run the command 10 times. Okay, let's run it. You can see that the CLI shows every time the command invokes the API endpoint. Great. Now let's go check the X-ray console to see if any data is there yet. So here is the X-ray console showing the service map view. Notice that I can set a time range on the view. This is set to show the last 5 minutes. And look at that. The service map shows that the API endpoint I invoked in turn invoked the getAllProducts Lambda function. Lambda shows up here as 2 nodes. The first one, called by the client, is the Lambda service. The second node shows the actual Lambda function I called. The service map shows the amount of time spent on each node. The Lambda service took 322 milliseconds to complete, but the function spent 260 milliseconds of that time. Well, I only invoked the API endpoint a few times. Let's give it a better stress test. To do that, I'll return to the API Gateway console and copy the invoke URL of the getProducts endpoint. Next, I'll return to my bash terminal and use a command called siege. With this command, I can invoke the endpoint more quickly than my earlier loop call to the AWS CLI. This command will simulate 15 users simultaneously hitting the URL repeatedly for 15 seconds. Let's run it. It shows a lot of 200 HTTP response codes. That's a good sign. Okay, now I'll return to the X-ray console and let's see what the service map looks like now. This time the test shows up as a different client. That's because I'm hitting the deployed API endpoint, not using a test invoke method call to the AWS CLI like I did in the prior test. This view shows that the API Gateway service is sending trace data to X-ray. Notice also that the Lambda service is taking a bit longer to reply with this volume of traffic. That's still pretty fast though. Okay, let's increase the load even more. I'll return to the AWS Cloud9 IDE and try simulating 50 simultaneous users. And now let's view the service map in the X-ray console once again. Remember, this Lambda function calls a DynamoDB database table. The numbers change slightly, but they stay in that high 200 milliseconds range for Lambda to respond. The circles remain green, which means that the responsiveness is within the specified parameters. Oh wait, I've refreshed the data again, and now just a bit of yellow is showing up. I'll choose the Lambda function to see details on that. Notice the response distribution view. It looks like the majority of responses were in that millisecond range. However, at least one response took about 3 seconds. Let's zoom in on that. I'll choose View Traces. Because I was zoomed in on these 3-second range responses, those are the only ones that show up in this view of the trace list. There were 5 of them. They all still returned a 200 HTTP response code, so they did respond, but they were just slower. Let's look at the details on one of them. And here is a map of this single trace with a timeline view. If I choose one of the status icons below, it shows subsegment information. Again though, there weren't any errors here, just a bit more latency in the response. Okay, let's go back to the bash terminal and test invoking a more complicated part of the Cafe's distributed application, the create report logic. Recall that the create report API endpoint invokes a step function state machine. Here I've got an AWS CLI command that calls that state machine and passes in some test data in JSON format. The command identifies which state machine to invoke by specifying the Amazon resource number, or ARN. It is again in a loop, so that the state machine will be invoked 10 times to simulate some load. That will give us some more data for X-ray to trace. Okay, let's run it. You can see that the CLI shows every time that the state machine that invokes the API endpoint has been invoked. Great, let's return to the X-ray console and analyze the performance of this part of the application. Let's look at the X-ray service map to see what occurred. Notice how this view is collecting, aggregating, and collating information from this distributed application in real time. As you can see, the state machine invokes 3 different Lambda functions and also sends an Amazon Simple Notification Service or Amazon SNS message with a link to the report. The state machine took the longest of all to complete, which makes sense because it doesn't finish running until all the parts of the workflow have completed. The Amazon SNS call was the fastest to run. It took on average only 48 milliseconds. The generate pre-signed URL Lambda function ran very quickly, as did the other functions. Let's return to the terminal and test a bigger load. This time I'll invoke the state machine 20 times. Now back in the X-ray console, I'll refresh again. It looks like the time averages to run each component are actually decreasing. That's great. I've been running tests for a while now. Some of the tests took a bit longer, so I paused the recording for a bit so that they could finish. But let's expand this result set here to include those tests. I'll change the time frame for the service to last 30 minutes. Now look at that. The other 2 Lambda functions still consistently completed quickly, but the average time over the last 30 minutes for the getRealData Lambda increased quite a bit. It took on average 1.19 seconds to complete. Let's choose the node the furthest to the right on the map. It took the longest. It's the getRealData Lambda function. Because it takes longer to complete, it causes the upstream nodes to complete more slowly. So X-ray helps me pinpoint a performance bottleneck relative to the rest of the application. Remember, this is the Lambda function that performs the database lookup in Amazon RDS to get the data that will be sent in the report. And here I can see that 89% of the time, this function performed well. However, it has an 11% error rate. I'll select the box next to the error response and then view those traces. Here I can see that 5 traces are in the dataset. If I group them by response time root cause, they are all part of the same group. I'll dig into the details on one of the traces in the trace list. Next, I'll choose the status icon in the Lambda function row that shows the red exclamation point icon. In this subsegment details view, on the exception tab, a message and cause show. It looks like a timeout error occurred, perhaps related to the database connection. This could be due to a number of reasons, and I could set up more specific tracing to get to the root cause of the timeouts. Perhaps it's due to a networking configuration issue between where my Lambda function is running and where the Amazon RDS database is running. Or maybe I should check my Lambda function code and confirm that the function that opens the database connection is coded outside of the function handler so that it doesn't close the connection every time it is invoked. There could be other reasons. Obviously, I would need to spend some time to look into this further. I could run more tests and sample a larger time frame. I could try to determine if there's a correlation between how many requests I run in a short period and how frequently this timeout error occurs. I could also use the X-ray SDKs to instrument my code within the Lambda function. This would provide even more trace data to help locate the root cause. I'll show you some code snippets in a moment that would get you started with that. But let's just take a moment here to recognize that by just checking a few boxes in a few AWS service consoles with no changes to any of my code, I was able to instrument many parts of my distributed application with X-ray. And X-ray has quickly given me insight into which parts of the application are prone to experience excessive latency or produce errors. For example, before instrumenting the application, I did not know which of the 3 Lambda functions was taking the longest to run. If the report did not arrive, I didn't know where to start looking. Now I do. I'd like to show you one last thing. Notice in the X-ray console, if I choose Getting Started, it prompts me to either launch a sample application or instrument my own application. If I choose the Instrument My Own App, it then prompts me to choose a language. I'll choose Python, and here you see that if I have an already built application in Python, I could instrument the incoming HTTP requests by using the provided Django middleware code. This screen also provides the commands I could use to download the AWS X-ray SDK libraries. If I import the SDK into my code, I could then update my application to use the classes and methods that the SDK provides to generate and send trace data to the X-ray daemon. Finally, there's code that shows how to run the X-ray daemon on an Amazon Elastic Compute Cloud or Amazon EC2 instance, in an Elastic Container Service or Amazon ECS container, or as part of an AWS Elastic Beanstalk application. The options for Lambda reference the documentation, which describes how to enable X-ray tracing on Lambda functions, just like I did in this demo. As you can see from the options on this screen, If you want to, you can configure tracing of events not only at the AWS service level, as I did in this demo, but you can further define custom traces in your application code. In summary, you've seen how to instrument a distributed application to share trace data with X-Ray from Lambda, API Gateway, and step functions. You've also seen how X-Ray is able to create a service map of the application to deliver insights into the performance of the different parts of the application over different time frames. You've also seen how you can drill down into trace data to gain insights about your application's performance. That concludes this demonstration. Thanks for watching.